Great. I mean, you can do one. I mean, you can leave for things. Yeah, do the changes. One. Okay, so let's start. So most importantly, homework 2 is finally out. And I wasn't slacking. I know. I hope right after the oh, I was worried about here, with all the plans and everything. Yeah, no, I started immediately after I left the lecture on Monday, and it took me, I was working almost the whole time on it, so it took forever to write. I hope, I mean, it will have bugs, but, hopefully not like a deal-breaking amount of bugs, so, but it's fun. And then I will try to, as soon as possible, but let's say maybe early next week, homework, which will ask you to build memory manager and learn how to build address spaces. And in order to figure out what does it mean to build an address space, today we will try to discuss what kind of operating system we're building, just to make sure that we understand what's coming next. Because to some degree, everything what we covered up until now, it's almost everything what, at some point you say, look, what else? Like I mean, I get it, I have to build a context switch. Philip's block roughly stops at this point, plus minor details, but we have to figure out what is that we're building. Okay, just a quick reminder. So it's on the screen, but let me draw it again. So what we aim to build is a microkernel. Does anyone know what it means, a microkernel? Not monolithic. Good. That's a language definition, no. Python prediction.
Well, when I read about this, I read that kernel to a user space.
Correct. So, I mean, you're right, Alex. So the idea is that, I mean, first of all, this idea was evolving, and it's still evolving. And maybe it's actually started evolving in a reverse direction. Let me explain. So originally, if we look at x86, right? So when we build x86, we say all the operating system functionality runs in the kernel. This is the kernel. What do I mean for that? I mean that if you have a device driver, like the network card, you will build a device driver here in x86, which will communicate with this device and then export. I mean, there will be a layer of network stack, TCP/IP, and then you will export some kind of a system call to the user level, right? And user will run as a process here, and like that's essentially this is what you've seen most of your life. This is kind of Linux. This is the process talks to TCP. TCP talks to device driver, network device driver. Similar in x86, we didn't have TCP and network device driver. Well, file system, but the file system was running here, and then it was a very simple IDE device driver, which was talking to spinning disks. Right? Makes sense? So that was the original idea from the late 60s, early 70s to kind of like build the kernel. The original idea was a little bit more interesting. They said, okay, you control everything through a shell, and a shell is like, this is what you interact with the common prompts, and then shell creates processes, they do something for you and send results back to you, right? We kind of know about it, right? So this is x86. At some point, they started thinking, okay, let's move all of it, or to some degree, let's move almost everything we can to user space, meaning that now, like for example, network device driver will run as a user space process. And operating system will provide an interface for this process to access the actual device. And typically it means that it will just map it, control, it's a memory mapped IO, and bar, forget what it stands for, but essentially when you write into those addresses, they reach device, and device can like do a send operation or something like that. And then through this interface, you can connect asynchronous communication interfaces like ring buffers and queues, which will contain actual pointers to packets. But the main idea that this now runs as a user process, right? Question. Sorry, I get this started.
Was the shell a special kind of process?
No, like not really. So it was using the same operating system interface, like the same set of system calls. It was maybe special in a way that it had some additional permissions, but on Unix, permissions are, up until the very last moment, they were so broad that all processes of a single user, of the same user, had the same permissions. Besides the root was privileged, right? Which is a design flaw, but it is what it is. And that's why in the x86 operating system class, like the undergrad, like whatever, just a regular class, we write our own shell and you can run it on Linux and you'll be happy. So nothing is special about it, right? Any other questions?
Before we go too deep into this, like, what is the argument for putting it?
Yeah, great. And this is actually my very next question was, I wanted to ask you guys why this idea makes sense at all. We discussed it a little bit, but
yeah, I think you discussed in the beginning, like, for example, having drivers outside of the kernel it lowers the surface area of the kernel being attacked because it's in user space.
correct. You get this argument. I don't know how, like modern kernel, like Linux, is 40 million lines of code. I don't know exactly the count, but I would say 70 to 80% of this code base, millions line of code, are device drivers. Maybe plus kernel extensions like file systems, right? That's not fun because who writes those device drivers? In a practical case, whoever builds the hardware has a division which writes device driver for this hardware. If it's Intel, then it's Intel. If it's whatever else, this is what it is. And some other people, right? So it's a distributed development, right? So the probability of finding a bug in those device drivers is obviously, first of all, it's hard to code them to begin with. And in the past, there were papers which were arguing that device drivers, by nature of their semantic complexity, meaning that they have to process, to some degree, process interrupts, do a lot of like low-level management of those queues, just because, you know, memory allocators and everything, like it's kind of like everything is written by hand and not abstracted for optimal performance. In part because this is like, this layout of this queue is also defined by the device manufacturer. And also like three arguments, so essentially. Lots of low-level optimizations, concurrency, and asynchrony. Asynchrony interrupts, concurrency means everything runs on multiple CPUs. So people were saying that device drivers in general have higher density of errors to begin with. And plus it's like a huge proportion of a kernel. Then kind of like some number of years later, so roughly speaking, if this is like 2000, let's say 10 years later, 2010, the argument changed a little because people came up with better static analysis, better testing, yada, yada. So essentially density went down. So device drivers had approximately the same density as other subsystems, maybe like file systems as well. But still, it's a huge fraction. So main argument for all these years was, guys, like, what's the reason to put it inside here? Because if you find a bug, typically you can like, sometimes not everything is exploitable, but if you chain multiple bugs together, you often can like escalate yourself to root. and own the system, right? Sure, that's the main argument. Make sense? Okay, so people started building microkernels, like pushing this outside. So Alex, this answers your question, right? Any other questions for this, for why to do this?
What is it, not?
Yeah, exactly. This is what it was. Good job. Like, this is what I was trying to explain. I will ask you this. I wanted to minorly touch on the second argument. So this is kind of like a role security argument. If you go to the security community or systems community as well, they will say, okay, roughly speaking, the solution to this is isolation, right? If you move those stuff in isolated domains, even if you exploit a bug here, you might change something here, and maybe it's a complete denial of service because the system doesn't cannot access the disk anymore, or like in this case, network stack, but you don't own the microkernel, right? And you don't own other subsystems, right? So your impact on the system is more limited, right? So this isolation was an argument for many, many years, and like the whole community was kind of growing on it, right? So, and stuff like that. But there is a second argument which like emerged not too long ago, maybe roughly again 20, like people started working in 2005. It took them a while, but second argument is verification. And it's currently like, it's an active area of research. The argument is that if you have a small piece of code like a microkernel, roughly the one which we did was 6,000 lines of code, but let's say a CL4 was more complicated, 10,000 lines of code. It became feasible to build a formal proof of correctness of this piece of software. If you trying to verify network device drivers or something, argument becomes much harder, right? So if this was like last 20 years, but maybe arguably kind of going away, or maybe becomes less relevant, or a combination of this two. So this verification is now. So the argument here is that by moving those components out of the microkernel, this microkernel becomes semantically simpler and can be handled with formal verification tools. Make sense? So that's the future is coming. Now the question is, so with all this beauty, why is that we don't run microkernels everywhere, right? So what's the argument against it? So
things may not be compatible, or like well need to work together. Like for your user space drivers, you might be missing, but seems like a rare case.
You thinking that, look, what if I wanna, that's a great question, but let's write it down here, compatibility.
Yeah, compatible.
And the way I will phrase it for you in a second is, how does it even work if I want POSIX or some kind of a like feature-rich standard? How can we build POSIX on top of a microkernel? I will put it here for a second, just because I want to like spend half of the lecture talking about how to build POSIX or how to not build POSIX, but build something meaningful, right? Okay, argument for compatibility is there, but that's not the main reason.
Speed.
Speed, exactly. So what's the speed argument here?
So I know that the Darwin kernel for Mac OS, they have a hybrid design with a microkernel and then POSIX implemented with the BSD link. And they used to have a stricter separation, but they decided for efficiency reasons to move some of the POSIX layer into the microkernel. So things I think like the file system were moved back in so that they have speed.
Correct. And I should admit, I mean, I would, if I were you, I would exactly repeat the same words. But if you start talking, at some point I used to know. I was working on the XNU source code. XNU is an open source version of their microkernel. And embarrassingly now, I don't remember anymore how it works. So I should go and revisit. So exactly what you said, but like to be able to like draw the entire map of the Mac system. And the same for Windows NT. So Windows NT also tried to be a microkernel and then switch back to hybrid, where components are like logically isolated, but run in a single address space. So attacks are still possible because this remote write is possible between these two. Okay, but why is performance, like at what point we lose performance? It's important to understand. So imagine, for the sake of the argument, let's draw a slightly different, like almost the same picture, but let's just extend it a little. And let's just, instead of network, we'll be using disks, just because we have x86, and x86 has a, like, remember, imagine we have a process. I mean, for the sake of example, let's make it a shell. And shell says open a file, like some cost. How does it even work on a microkernel? Where is the file system now? It used to be that open was going to the kernel. There was a layer. Remember the layers, like name I. Okay, syscall, name I. What's next? If we go, file descriptors. Then what?
Directory entries.
Yeah.
Or it was the path name used.
Yeah, maybe part of name I directory. File descriptors, then like transactions for logging, and then buffer cache, and then this driver, right? And then it was talking to actual, sorry, that what the country, and then it was talking to spinning disks, right? So how does it work in this microkernel setup? Yeah, so how?
So I'm guessing all of this functionality will be in the user space process.
Mhm.
It will have a user level buffer cache, I guess. That's
Right, so depending on how aggressive we are, we can either split those layers in multiple processes, but let's at least roughly speaking say that file system runs as one process, right? So this is file system, and the disk driver runs at another process, right? So this is a disk driver, and it talks to spinning disks. And the question is, how do we now communicate? How do we even like communicate between, when you do open, apparently open has to land somewhere here in a file system, which implements open, right? And then it will be doing like name I, right? Name I, whatever, file descriptors, whatnot, buffer cache, loading German. Buffer. So how do we communicate?
Like we talked about this, and like you and I in your office, the only thing that knows about all the processes is the kernel. Like, that's my understanding. So you have to go.
I'm thinking shared libraries.
Jesus, shared libraries.
Is that bad?
Bad. Don't say this.
So you don't like libc, is it?
No. Like it's just like not really related, but we'll come back in a second. But just for the sake of example, again, just to make it concrete, imagine this is using regular ring-free page tables, and this runs in ring 0, right? What was the option to communicate between two processes in x86? What was the communication mechanism? Pipe, right? How did it work?
The file descriptors were like the input descriptor of one process was.
But
Are there buffers on both sides?
mechanically, we were doing a system call, like literally invoking in the 40, x40, right? Dropping into the kernel, passing some arguments. Those arguments were placed in some kind of a buffer, which was in the kernel memory, right? And roughly speaking, we were returning here. And later on, the file system says, I'm ready to receive it. And whatever, it was read and write in case of a buffer, but here, imagine we are sending messages and we say send and receive. But again, to receive, you also dropping into the microkernel using an int x40 or sysenter instruction. Sysenter is a little faster, we'll be using sysenter. And at this point, you, like, whatever was written in this buffer is now read back and appears in the memory of the process, right? Okay, sure. And then if you want to send something to the disk driver, you obviously do another send here. There is some kind of a buffer in between them. And this guy later on says receive. And at this point, you know, you get this buffer here, and maybe there is kind of like some kind of a communication with the actual physical device, but it's kind of like DMA. So that's probably almost the same speed as everything else, right? You get the point. So now you have to, if you just simply running green 3, you have to do syscall 1, syscall 2, syscall 3, syscall 4, instead of just a single one, which was here, right? And also, syscalls themselves with sysenter are not very expensive. They're only like 100 cycles, let's say 120. So, but still, you increase the price from 120 cycles here, because normally when we were doing like one syscall, and this was just a function call, right? And function call is like 5 cycles, right? Roughly speaking, push the arguments on the stack, or it registers. Like if you maintain the stack frame, roughly, let's say 5. So it grew to 120, 120, 120, 120. So grew 120 by 4, right? So roughly, what is that? Whatever, 480 cycles. That's okay, but not super horrible. But what's worse is that every time, if you're running on a single CPU, every time you want to switch from this process to another, you have to do a context switch. And the expensive operation is to switch address spaces, like really, like I can say flash TLB, but TLB can be tagged, so you may not flash that, but it's still expensive. And so roughly speaking, one round trip for send receive, like essentially one crossing between these two will roughly be 1,000 cycles, right? And you have to do 2, 1 and 2, right? So if we count these plus address spaces, we're roughly to 2,000 cycles, right? And this is where the performance was like going, essentially sending those messages between isolated processes, isolated with those ring 3, with like regular page tables, was killing performance. It was tried in like early microkernels like Mac, which was later used by Mac OS and free and what else? And Windows NT, right? So, but this is the performance argument. Communication is expensive. Like that's essentially what you have to remember. And you have to remember the mechanics of this communication, that you have to exit into the microkernel, copy some stuff between the, like into some buffer, and then exit and then enter from another process.
So from a microkernel, I would assume that system calls and context switches would cost less because it's a thinner kernel, it has to, there's less overheads.
Correct. And those numbers I quoted for the very fastest microkernel, the CL4. The CL4, those guys are proud of their numbers. Although realistically, you can achieve the, like in this kernel, which we can end up building, we will get the same numbers, plus minus like 50 cycles.
But you say these numbers are faster than
Linux is like 10,000 cycles. Not 2,000. Just because of layers of overhead. But and that's a valid question. But Linux was never designed for fast communication. And maybe I mean, maybe that any new microkernel would be, right? Linux was.
That's my individual components of my driver. So I trust my file system and this driver. There should be a way like an IPC, right?
And this is the IPC, right? What I was rolling.
I don't need to go.
Yeah, you say you can merge them, right?
Kind of.
Okay, so what happens when you, and that's a valid argument. This is this hybrid design. So hybrid design, which Alia mentioned, and or maybe Alex, is at some point the performance was killing them, and they said, "Okay, guys, it's nice, but it just doesn't work." And they moved everything, all of it. Maybe the code base wasn't even changing that much, but they moved everything in ring 0 back into the ring 0. So now this and this runs in ring 0, right? Now this send, instead of like going through syscalls and address space, which is just a function call, it still takes some time for me to copy something into the buffer, but it's roughly maybe like 50 cycles, right? And so this is where macOS is running, and specifically macOS, because macOS runs on top of a real microkernel Mac.
That's probably when it was trying to have like shared buffers.
Yeah, we'll come in a second. You're right. So let me, but what I wanted to finish this argument, which I started. When you do merge, you obviously lose the fact that if there is a bug, imagine it's a buffer overflow for the sake of it, right? Which gives you, let's say, a write primitive, writes anywhere in memory, then you can reach any merge subsystems, right? You can reach with this. If you have exploitable gadget in a piece of code here, since there is no address space isolation, you can reach address spaces of any other subsystem. So it's a trade-off. It's a performance versus security, right?
That's why I was thinking of the shared library approach, because they share address spaces, but still have some isolation in terms of execution. That's what I was thinking, but I might be wrong.
Well, you like let's introduce the shared library into the figure just for the sake to answer this question. Imagine you have some shared library. For the sake of example, let's imagine it's even printf. Right? It can be something else. Maybe we're computing some secrets with whatever, some crypto algorithm. Let's just keep it simple, printf. Shared library, what it does is that it maps single region of physical memory, which contains the code of printf plus, what is it called? The table, global offset table. Global offset table. Jesus, like the GOT is not shared. Just let's not overcomplicate. And that's sharing. This is the text section of a code, right?
Yeah.
The data sections will be private because I have a variable 8 equals 1 here, and here 8 equals to 0, just because I didn't do something, right? So of course you share the code section.
Yeah.
But it doesn't help you to avoid this IPC because you just like you gain something by sharing memory and like using class memory. But if you need to send this buffer across, just because you say
like it would be faster as a function call. And like we saw that function call has a lower cost. So we could exploit function call.
yeah, let me explain it differently. Imagine this driver has some kind of either a RAID capability or, for the sake of example, crypto.
Yeah.
Meaning that it doesn't encrypt all the traffic down to the disk. And it's a system critical component because you say, look, you have to encrypt and no one else can like access it. There will be a key, right? This key is physically here. And you cannot, the moment you're moving it here, your trust domain expands here, because if you have a bug and you can steal a key here, then you lose a key, right? That's why like isolation is, to some degree, isolation is semantic. It's just that how it maps on the, but semantically, it's like, I don't trust you and I will ask you to do something, but you provide a very narrow interface for me, like encrypt, decrypt, but you can never read the key, right?
Yeah.
And this is all these attacks like Heartbleed and everything, right? Because SSH is mapped into your address space. You find a bug in some logging library, which you downloaded from Rust crates or something, right? And then it has an exploit, right? So if this other crate which you're running would be running in a different address space, for that Rust crate, reaching that key would be much harder, although not impossible. But it cannot be reached with a stray memory read or memory write, right?
Sure.
So are we on board with this? Okay, we got the performance argument. We got the trade-off. We say, look, it's a trade-off, like splitting versus isolation gives you more security and maybe arguably more reliability, because there is an argument that you can restart some subsystems, maybe not all, like network drivers, clearly restartable because you just lose some packets, which is anyway okay on the, like restarting the network stack probably is much harder. So maybe this argument is not even true, but like at least people still believe in it, or like would come to believe, right? And I said, and this is what like if you see like recent developments, like Google is building a microkernel, like Fuchsia or what's Magenta, right? Or whatever the word, the name they're using now. Who else? Maybe like everyone building hypervisors, obviously, but maybe not many people build microkernels, but microkernel is this idea. And I said that maybe this idea was evolving. Essentially, people were saying, okay, move as much as possible outside of microkernel. Again, to reduce semantic complexity of the code here, reduce this physically probability of finding a bug, just because less code you have, less bugs you will have. And now, with this verification argument, the whole story started like moving a little bit backwards, because people said, look guys, we already can verify the entire microkernel. And of course, performance argument is killing everyone. So, but our verification capabilities are so powerful these days that we actually not too far away from verifying like a network device driver. So why not to move it back into here? Because if we have a formal correctness of it, we know that there is no bugs. It's guaranteed by the proof. I mean, we can make a mistake in specification, and then there is a bug, but you know, probability of this, it's non-zero, but it's lower. And so when I said that maybe this microkernel argument has suddenly started like moving in the other direction, the only answer is because of verification. Make sense?
So then NVIDIA's device drivers will never be back in rank 0.
Supposedly, unless they open source them.
Clause.
Yeah, that's one argument, but I also think that they are so complex, you cannot verify them. They are really like, even like, One Week was recently looking at the network device driver for like 100 Gbps network interface, and it's 200,000 lines of code. It's beyond the reach of verification. We can physically handle 10,000, but it's like another order of magnitude. And I don't know where we will get to this another order of magnitude. Even this 10,000 is hard. I mean, maybe like we can verify like clean sequential, semantically simple code, but that's usually not the case in device drivers. So I don't know. Yeah. So anything, but Talia, there is another argument if you want to hear. I apologize. You can come up with the proof, and you can use something like typed assembly language or some other abstraction which allows you to verify that proofs holds without revealing the source code of the driver. So PL people, PL people are suddenly excited. No one else is excited, but it's doable.
Yeah, that sounds like a pain in the ass.
Yeah, I know, yeah. But you get the point. So closed source versus open is not always a deal breaker, but it's hard. Okay, hold on. So a lot of like background here, but this is what we're building. But just to get a cleaner picture of, and hold on, one other thing which I wanted to say, which I wanted to mention before we move on forward, is that like in my story here, I said that if you do an int or a sysenter to switch privilege levels, right? If you carefully look at this picture for some time, it starts occurring to you that you can come up with a hardware primitive which allows you to implement kind of like a protected function call in hardware, and it actually existed on Intel, which I think it was called something like Volgate what these are, I don't even know, but they like, if you read info documents, there will be a code name. But essentially, but there are other mechanisms which, if you carefully think about it, you can come up with a magic, I don't know, X-call primitive, which switches the address space for you without actually going into the microkernel. And then this one can theoretically approach the overhead of a function call. Right? So roughly speaking, like maybe even 5 cycles. It's just that you spend, even if you're just saving and restoring general registers and switching steps because you don't trust the stack, right? Because you cannot just pass a pointer to this stack. It takes you roughly at least like 50 cycles, but even this can be optimized in hardware. So if you're a hardware architect and you're working on something like this, it kind of would be a cool feature to say, look, I actually can come up with an idea of how to switch those address spaces without doing this detour. This way of switching address spaces is called exitless, because you don't exit from ring 3, but just switch those address spaces. And maybe this protection boundary is not even page tables, but something else. And DL people immediately gets excited because they know something like, they know what binary rewriting is. And they say, look, something like software fault isolation is a good candidate to enforce those boundaries, or maybe software fault isolation plus some hardware primitives, or maybe some funky hardware primitives which allow you to do this. So there is a research area which tries to do this. And maybe, I mean, I don't know why everyone is stalling on this. So it's not as hard to build, honestly, but it's not as easy either. And then you might get a CPU which changing protection boundaries is roughly as expensive as a function call. And then you back to this argument that, isolation is free, right?
So if it's easy, can we do that for expert?
Yeah. Someone is already, from a previous version of this class, someone signed up to do it as a project. It's still not done. It was rejected once. But you can, if you're interested, talk to us, and we're always looking for people. There are some nuances, but I think we have a decent amount of knowledge to solve the nuances, but it's still okay. But you got the point. So Intel is stalling. So other CPUs, Intel is not fully stalling. So Intel has memory protection keys. Is a light way to implement this isolation boundary. ARM has memory tagging extensions, which allow you to build faster SFI, hardware accelerated SFI. And ARM has PAC, which is a crypto scheme, encrypted pointers, which kind of also can be used for SFI plus hardware accelerated SFI, except that it's at least slower than non-accelerated SFI. I don't know. I'm not exactly sure why PAC was more like, let's enforce safety in hardware. Okay, but this is also clear, right? So there is a direction of work which says, okay, look, guys, we will erase those isolation boundaries, making them lighter. And then microkernels are coming back. So this is why it's all still makes a lot of sense. But now hold on, like back to the main line of our class. It's related, like the main question we're trying to answer right now is, what is that we want to build? We want to build an operating system in style of a microkernel. Everything runs at user level. The question is how, and specifically, imagine we have memory allocator, and we know how to build the very first process, the address space for this process. What is that we're going to load there to make sure that the system can run and do something similar, something meaningful, meaning that maybe create other processes like P0 can create P1, and then they communicate, and an ultimate goal is to build something like, I'm not saying we will be able to build POSIX, but at least let's imagine we want to build POSIX, and let's have it as a plan, but we will quit early. So back to this question. So how to build POSIX on top of this? Oh man,
Maybe I should ask what I've encountered POSIX before. I still don't.
well, yeah, me neither. Don't worry. So it's a collection of syscalls which you typically see on Linux, although it's like POSIX-like subset. It's not official POSIX, but kind of like open, close, send. Oh, what is send? Oh yeah, send, receive. In terms of network packets, like fork. Fork and exec are the hardest features of POSIX, so we're not going to build them. But those, like essentially x86. When I say POSIX, let's just say x86 to make it concrete. So how do we do this?
Just put some pointers in every process leads to the functions.
It's not as naive, right? You're right. So file systems, when you say open, now this guy open reaches the file system has some file descriptor table, knows what to do, right? What happens when you do, like all the file system calls essentially go to the file system, right? When you have something like, well, let's say exec, now what? Where does exec goes?
So is the problem that you don't know statically which process is the one to handle the file system?
No, let's imagine we know. Like we have typically this IPC mechanism I'll be using the word endpoint. It's kind of like a file descriptor into which you send and receive messages, but you know them, you know what they mean semantically, right? The problem is that this process, do we need to go to file system to implement exec or not? But then
to read the binary.
oh yeah, this is yeah. To be honest, like when you said yes, no, I was also fully what should I yell? It's a little bit more complicated as complicated compared to very naive, like immediate answer. Meaning that if you want to create a new address space, like imagine empty, you probably have to go into the microkernel with a syscall, which will give you a new address space, right? Okay, but then you say, look, but we'll copy my memory from here to here. Or sorry, like you say, exec doesn't copy memory, it's fork, which does. Where is the binary for, like, I don't know, VNLS, for example? Binary sits in the file system. So you really have to like go to the file system for some kind of, it's not open and close, it's some other protocol kind of like, no, you probably can actually do open internally. And say, look, give me this file. You can read the entire VNLS into your address space. Like this is the last temporarily here. Then what happens next? How does it end up in this address space?
I would, like, the way I would construct it would be, I assume we have a user space scheduler as well, which is managing processes. The scheduler will do the syscall for memory. The scheduler will hook into the file system.
Oh, what Soham is, he's like trying to find holes in microkernels, in our beautiful microkernel. He says there will be
a user space scheduler.
no. Soham says, okay, we're gonna start like a very powerful process, which he calls scheduler. That's to confuse kernel number two. That's to confuse the attackers. And he says that scheduler has somehow all the memory of this process is mapped. It's in the kernel, but now here. So now if you find a bug here, then yeah, I'm sure you can control this. So I mean, it's one way to build that, but maybe not the best. People will push back, right? Although like it's not really a scheduler; it's just more like something which has all the memory. Because scheduler,
it is doing this, like it will handle context.
no, context switches are here.
Or they still have to be in the context.
Not strictly speaking, but if the timer interrupts, typically microkernels implement the timer interrupt, and like literally, like they control the CPU and they will save the execution context and switch to the next one. The decision which process to run next, for example, if you have a very complicated like fairness policy, then you can push it outside and see, okay, you decide who runs next, you just give me the like whatever this queue, like you compute the queue yourself, because it's kind of complicated logic if you really want to like implement several policies, right? Okay, sure, that idea we nuked it. So again, back to this, how does this ls gets either from here or from here into this address space?
Does it need a syscall? Because it doesn't have access to the other process's memory because of address space separation. So I think the kernel would need. Right?
Yeah, you can ask to kind of like mem copy here, right? Something like this. Is that what you're thinking about? That's a very powerful mechanism, and then you're risking that maybe someone can abuse it like this. I mean, I don't have a very good concrete argument, but if you have this mem copy, it probably should only work at a specific moment in time, because later on you don't want this process, maybe it's like mission critical process, and it like runs something very important. And someone like overwrites it, it's like that write primitive. It exists through it just goes like it's more like a confused deputy problem. This thing always happy to copy, but someone has to check whether it's okay. So
So for open, you said that we can have sort of like a function in the file system process, which is directly called by my process.
yeah.
So what if when we request a new address space, we define some sort of boilerplate code segment, text segment for this new address space, which can at least call file system.
Yeah,
So
and
then
that's
instead of copying the binary over, this can load the binary directly.
and this is actually one of the ways I suggest to build it. So what Soham is suggesting is that every new process, every new address space has some kind of a tiny boot code.
Yeah.
And maybe we will get when we create a new process, like our create process or create address space, no, let's say create process. Create process system call returns the caller an endpoint. And this boot code starts listening on this endpoint. And this way we can implement a boot protocol, which, for example, receives this ls into this address space, right? And then if it's like complicated, if you need a linker, sure, then it's multi-stage protocol where you first like copy the linker, then you copy more, then you relocate stuff, then you copy even more libraries and stuff like that, right? So it's kind of self-bootstrap, right? Makes sense to everyone? That kind of like, that's okay, I would say. It's a very narrow protocol because you say, look, everyone trusts this well-known boot code, and then it follows, we can verify it, it follows this bootstrap. At some point it reaches main. And if you don't, and maybe typically, maybe if you want to talk to a file system, then it's a what is it, responsibility of this parent to pass an endpoint through this endpoint to talk to the file system. Otherwise, you don't even have an interface to the file system of this system, right? You bootstrap, but you cannot talk to the outside world. The moment the parent kills this endpoint, you're completely isolated.
I was thinking the bootstrap would include like crucial functionality like file system.
Or file system,
Or just those function endpoints, like the same open endpoint, for example, if that was available in the bootstrap.
right, hold on. Okay, and maybe it wasn't clear. These endpoints, you can think of them as magical pointers in this system, which connect. If you don't have one, you cannot just figure out how to talk to file system.
Right, but is that pointer coming from
From the parent.
Oh, that pointer is coming from.
If the parent sends it to you, then you have. It's kind of like you create a class in a type-safe language, and you pass certain arguments to constructor. If you don't pass a pointer, if this language doesn't have global variables, which typically languages have, but let's imagine we figure out a language without it. There is simply for this class foo, which takes an endpoint, let's say one endpoint when it was created, and this connects it to whoever called the new, right? Then for this code inside foo, there is no way to get access to any other endpoints in the system or pointers in a safe language, right?
True. Well, I was thinking that the file system, like the open and close functions, for example, would be exposed as.
Okay, so
I don't know what.
no. You're kind of right about it, but we should talk about it, but probably a point of a different discussion. But this idea of passing those like, I argue that you guys think in terms of a language. So if you have a pointer to talk to something, you can. You can receive back more pointers from this someone if it's willing to share. And those pointers, I will draw them like this, will lead you to some other parts of the system. It was A, then this is B, B may be connected to C, right? But think of a language, and essentially, if you have a pointer, you can access the object.
Sure.
This idea is called object capabilities. A capability is a pointer. It's kind of like in a security community or in access control community. This pointer gives you a right to execute something and access some piece of data which is attached to it, right? Which means that if you don't have an endpoint, which in our system can be a pointer, to talk to the file system, you will never get any files, right? Whatever you were launched with, whatever the parent wanted to share, then this is a powerful idea. And for example, this idea of, it's kind of like completely reversed from Unix. In Unix, when you start a process, everything is available. You really have to heavily work to restrict it, saying, okay, this is disabled, and this is disabled, and this is disabled. This is the opposite of this idea, is nothing is enabled. If you want something, you have to pass it explicitly. And you say, look, what if it's a crypto library, and I just like, I really just pass my key inside, and it encrypts. I send text, it sends back encrypted text. But the attack surface on this process is very, very small. Meaning that, like file system cannot reach it and exploit it, no one can exploit it, right? So it's kind of, it exists in your system, but no one can reach it. And this idea exists right now in industry, like in Amazon Cloud, where they're using this, what is it called? What is it called? I forgot there.
Is it Pledge, like PSD?
Is it what?
Pledge?
I don't know. I don't know the name. It's more like in macOS, there are capabilities these days, I think, but I don't know how they implement it. No, I wanted to say they have this Nitro hypervisor, and they use, like, they have an idea, they will market it and send it to you, a virtual machine, which is completely disconnected from the outside world. Like literally, only the hypervisor context switches it, but nothing can like reach it. And they say it's like, that's to protect your secrets. But hold on, this is a powerful idea that we're going to build this as a connection of those endpoint graphs, right? And this is one way to boot the system. An alternative way, which is conceptual in spirit and maybe simpler, but maybe a little less secure, is to allow, like, actually probably it's still better to use this idea. So part of the boot protocol can be, for example, establish like the child, for example, can share its entire memory with the parent through this endpoint, because it can send pages or like send share my page requests, and then the parent can do linking and loading on the child, and then the child can map the pages. That's another way of doing it. But hold on, you got the point. So it's kind of like at a high level, it's a self-bootstrapping thing, right? The reason I spend so much time is that it's not a coincidence. This is how I want to build it, because it's a microkernel, right? So there is no, like, nothing is there by default. So we just build everything ourselves. And the idea which I'm kind of like pushing is that if we have a microkernel, the thing into which we boot it, right? It can, for example, have like, imagine this is like, roughly speaking, the file system or an image, kind of like a ramifas or something. And we can play the following protocol. We say, look, the microkernel, when it creates the very first process, the very first address space, the protocol will be that this blob of memory will be copied, mapped and copied at a specific well-known address. I don't know, let's say ABC. And microkernel will jump to the entry point of this ABC. And then this thing, which we will call domain 0, for example, will start living, and will starting other processes by saying, like, kind of create process get a new address space, get a connection, like an endpoint. It's kind of like how descriptor 0, kind of you can talk to your child, right? Similar to how when we fork. And then like if this image internally also includes like images of other processes, right? So for simplicity, because it's very easy to build, it doesn't have to be on disk. Of course, we can think of how to like talk to disk and stuff. But for example, it says, okay, my next thing is to start a shell, some kind of shell. Let's say we don't know yet what it is, but essentially it says, okay, in this image, which we copied here in this file system, there will be a shell, and we will copy it here and essentially start running here. So that's how the system boots, and essentially they all, and then it's up to you how to design this protocol, but our goal is to just start a couple, so the whole the whole thing starts running.
So, will these connections between processes always, like, do we need them to, like for example, if imagine we create a whole tree of processes, and one of the processes in the middle terminates, just because it competes. So then, do we lose access to certain active processes?
Probably you can have a system in which you can build something like this connects to this, then this connects to other things. And the expectation was that then like if you want to talk to let's say A and B, C and D, if D wants to talk to A, it always goes through C, maybe C like some kind of a like security service which decodifies information. And if C dies, then A and B are orphans, and we can choose what to do with it. We can make a decision, but yeah, you can lose a connection. But it's the same in x86. If you suddenly, if three processes connected through a middle process through a pipe, and the middle one dies, and the edge ones cannot talk to each other. Agree with this?
But at the same time, like when the process is created after exec, it's pushed into the process table as well.
Right, but they can never figure out each other's file descriptors.
Yeah, they can't figure out each other's file descriptors, but at least like it can context switch back.
No, they are running. So D and A and B are scheduled, but D cannot get to A and get like, think if this is process 3 in x86, and this was a parent, this was a child, these were other children, this died, this cannot connect to A and B.
Yeah, the communication aspect I agree with.
Yeah, but they continue running.
But they got, and we can still access them as it, like would I be able to polish that into?
You will be able to see it on like talk probably, but you will not be able to get any information. I mean, you can come up with the protocols. I mean, and first you can make different design choices. You can design a system in which if C dies, all the children are. But that's probably not very practical because sometimes C wants just to exit sometimes. But hold on, I wanted like any other questions. I mean, in reality, the reason I spend so much time on this is because I want you to build it. So the very first address space will come up with a way to have some kind of a repository. It's not a file system, but something of individual processes like a shell. What is a shell? I don't know, like something that will be printing for the world. I don't know what else. We probably will not be able to build a file system, but at least we'll have some toy processes, P1, P2, and P3. And the boot protocol will be that the microkernel will create this very first address space, domain 0, loads this thing inside, jumps to the entry point, and then this thing evolves on its own, invoking the system calls of microkernel, kind of like process create, thread create, send, receive, connect to this IPC mechanisms. And we will probably implement some kind of this self-booting protocol for temporarily sharing of pages between parent and child. And this will allow us to boot the system, right? Because in x86, the way x86 was working is that it also had a very simple trampoline loaded in in the first process immediately exec, and it exec into init, but so since the file system was already running, file system went ahead and just like grabbed init from disk. Also x86, since it was an exec, was implementing minimal loader, so it was actually able to load init into the address space and just pass arguments, stuff like that. So in a microkernel, we will try to avoid doing it, pushing all this linking and loading into the user level. So really create a process will be an empty address space, maybe as Soha was suggesting with a tiny boot trampoline, which will map in every address space. And that's about it. But this still allows us to build a fully functional system. And if we're clever enough, we can even build POSIX on top of it, but probably we will not. But at least like it's practically possible. Okay, makes sense. Any questions? Okay, so this is the thing to remember. So because immediately, to be honest, I would even want this maybe to be included in homework 3, because I want you to immediately the moment you have a memory allocator, I want to create a very first process. And until we agree on the boot protocol for this very first process, like what is actually running there, it doesn't make sense. But essentially that's the agreement. So that's kind of roughly the scheme. So maybe I will write it down in the homework, but we will build it. Since we still have time. Now the next question, although everyone. I exhausted you with this conversation.
Exactly.
What is it? What exactly is what? Linking and loading?
No, the link.
This link?
Yeah, like what is that?
That's a good question. So that will be maybe homework 4 or homework 5. The one of these to build this link. That's a good question. So let's think of it. So what do you think it should be? While I'm erasing.
We mentioned expo.
Well, expo is fantastic, right? But you know, we'll never finish the class. Yeah, not today. I mean, I want it for each of you, right? So even for PL people. Okay, wait, hold on. What's the interface to this? We've seen one thing like that in the past. It was a pipe, right? Literally, the interface to this link was read and write into the pipe, right? And that was a buffer in a microkernel or in a kernel of 512 bytes, and so this guy can read and write into it as well. What are the advantages and disadvantages of this mechanism?
The disadvantage seems like you have to go into the code to read the values. So
Right, and I don't think we can solve it without this new funky mechanism. But it would, yeah. So that probably is there, but thinking of the interface. So we kind of like do a read of some kind of a, what is it, plain old data structures, kind of like, it's just blobs of bytes, and we write them, and we have a queue here.
It's also, if I'm not mistaken, the pipe is sort of like a one-time communication channel.
What do you mean one time?
Like parent process will do, or like it will do all of its writes, and then the child process will do all of the reads.
No,
So
no, it can like push a couple of writes here, and then this guy can come in because we context switch between them and do a couple of picks up this too, and this one will add more, and the other guys will pick them up. So it's essentially.
I guess if you like spread out your reads.
Yeah. Okay, so to be honest, pipe will work. What I'm trying to argue for is that in those microkernel systems, people were trying to kind of make everything as simple as possible. Again, easier to verify, but But also pipe doesn't give you like a lot of tremendous advantage on top of a different mechanism, which we will try to build. And again, it's very useful questions. I kind of maybe it's a good idea to discuss what this is. So I suggest to build the following mechanism, and this is what like other microkernels are doing, like a CL4. To build this thing, and I call it an endpoint, or another name is rendezvous endpoint. Someone has to spell it. Yeah, I'm not going to try to spell rendezvous. The use case, the primary use case is calling a function call. So imagine this guy implements a function call, and let's say this is a server and this is a client, and a client wants to call foo, right? Essentially, like it can be open, for example, like in terms of a class system. Open. Implementing this call open on top of a pipe is possible, right? You just like serialize whatever, some kind of a JSON-like IPC, or maybe a minimal thing, open, serialize some arguments, right? But then really what you want to happen is that immediately after you call open, drop into this microkernel, ideally you would like this guy to start running immediately, right? It's also achievable with the pipe, because if this guy, which implements kind of like a server dispatch loop, says, okay, I'm ready to read from a pipe, or in terms of messages, ready to receive, right? It's already hanging out, waiting on this open to show up in a buffer. And the moment this open goes in, well, it gets unblocked and maybe starts running, right? But ideally, it also makes sense to kind of like even implement a context switch here, to switch the address spaces, meaning that the moment you say open, it goes into the kernel, records the arguments, and immediately switches from running process P1 to running process P2. So essentially, the context switch in the kernel, the schedule in the kernel, immediately picks a process which was waiting on this endpoint, right? Which is slightly different from a pipe. And the only real difference is that there is no buffering here. And instead, we say this buffer can contain only one message. Like roughly speaking, we can say, look, it can contain, I don't know, let's say 32 registers of 64 bytes. And those registers can either contain like just numbers, roughly speaking, or you can encode strings. And maybe some subset of this register, kind of like maybe one or two, can also allow you to send a page across, meaning that if you send a page, you record the fact that the sender is willing to send a page, and the receiver picks it up, and this page is mapped into the address space of the receiver, right? This allows you to share memory across processes, and then later on allows you to like establish a larger region of shared memory. And then if you want to send a lot of bytes, you can implement your byte buffer here in a shared region of memory, but maybe it will be like 1 megabyte in size or something like that, right? So this mechanism is sufficient. So it's much easier than a pipe. It only allows you to do one message. It supports a send and receive interface. And on top of it, you can build like synchronous function call invocations. And if you need a lot of data, you first like push a bunch of data. You first establish a region of shared memory, then copy a bunch of data here, and then signal to the receiver once, right? So that we can talk about it like in a separate lecture, because it's kind of important how to build it. So it will be a separate homework. But at a high level, the following things are important, kind of like a synchronous send receive, abilities to send scalar, like just integers, but also roughly speaking, pages of memory. Pages of memory is important to establish larger shared regions of memory. And then if these two guys are actually running on two different CPUs, You don't even have to exit into the microkernel, because the moment you put something into this region, the second guy who is running here can look into this region and pick up those, right? So you never actually exit in the microkernel unless you need to signal, right? Make sense? Okay. Okay, since PL people started leaving, I should probably stop. Okay, so I don't know how well this came across, but we'll come back to it. We'll design it. But that's, at least at some point, like, it's powerful enough to like establish shared regions, and it's powerful enough to implement synchronous system calling, like function call invocations. And it's also elegant enough in a way that if you magically come up with this X call primitive, then you really, instead of call here, you can put X call, and then you can just bypass the microkernel and like even save a lot on synchronous invocations. So, but we'll talk more about it, but let's just have some outline of what's coming. So,
Yeah, I'm still thinking about like the graph of all the processes kind of connected by a link.
yeah,
Now, it is possible that from process A to process, say, F, there are multiple paths.
yeah,
Would it be, and say one of the paths breaks because the process dies?
Yeah. yeah.
Could it start leveraging one of the other paths through other processes?
Well, probably, but let me.
Is that like,
I think it's, wait, hold on. So I think it's a slightly wrong way to go. So let me like use this last 5 minutes on one kind of very important idea. One important idea which might resonate with some of you because you work in this, for why people wanted to build those microkernels is the following. Like I get it that you're kind of scared that now everything looks like a graph.
yeah,
And you never thought of how to even build the system as a graph, because in Linux, everything is like kind of flat
yeah, it's a
and everything is accessible to everyone, right? That leads to one inherent problem. In Linux, it's impossible to implement something what is called a partitioning microkernel or a partitioning hypervisor. Meaning that you say, look, I want to have a very strong guarantee in a mixed criticality systems, like think of automotive, for example, where you're running in a collection of cores. But now it's, let's imagine you said, okay, I bought like one Intel board instead of like hundreds of different microcontrollers. And this runs my multimedia system. Like everything what you see on your screen. But those tiny little processes here, they steer the wheels. I don't know, process down data from the sensors and everything, right? This line partitions the system in such a way that no matter what this multimedia subsystem is doing, like how much CPU resources it's eating already, how frequently it calls the microkernel, it cannot affect this partition, which is a mission critical partition, which steers the wheels. So it can crash, it can reboot, it can do anything it want. But the system has a guarantee, either formal with a proof or informal, like just an informal argument that you convince someone that this microkernel is clever enough to never allow this process to somehow affect execution of this process by introducing a ton of interrupts or exhausting all the system memory or monopolizing the CPU because it created a very large outer space, which is a little untrivial. So imagine this is a page table. It's a giant page table, like maybe gigabytes of space. And then it says something like unmapped. And it takes forever to execute the system call. If you're firing some logs, maybe it will interfere with logs, which will be here, right? It's a totally non-trivial argument in practice, although it looks simple. And in practice, building this on Linux turns out is impossible. So Linux by design doesn't have enough kind of baked in isolation to allow to make sure that you can implement this partition. So Linux was extended with ideas of containers and what do they call them? C groups, right? So essentially it does provide isolation, but it's still soft isolation. It's almost, there is no mathematical proof And I'm not an expert on it, but if you start thinking hard, you probably will always find some kind of an interrupt comes in, starts executing here, reaches other partition, and then whatever, delay of 200 milliseconds, and this thing doesn't steer the wheel, right? So it's performance isolation as well, not just like exhausting, like functional. So microkernels were those, if you kind of flip the world around and say, look, microkernel is my starting point, then you can come up with a system in which this partitioning is enforced. And then truly those two graphs are never actually connected, because this domain 0, which maybe existed ran in the past, created these two partitions, like gave half of the system memory to one partition, half of the system memory to another partition, and then exited, or just you have like, or it says halt and never does anything, then these two guys run in isolation. That's another powerful argument for why one might use microkernels. So we didn't talk about it, but it's real in practice. And it's real in this automotive market where they say, we used to run hundreds of those microcontrollers, but now we want to put everything for one on a single board. Can we do this? And the answer is not, you cannot trivially do it. They usually, these days, they usually put, instead of a microcontroller, they put a hypervisor, which runs one Linux and then some real-time operating system. Okay, cool. So let me stop here. So just for the sake of simplicity, so can I assign homework 3? We'll see how much of it will go in homework 3. Maybe almost nothing. Maybe we will just simply allocator plus empty address space is homework 3, and homework 4 is like load this, create this file system, and copy it into this very first process, right? So this is how we will start. I also wanted to discuss which system calls we will be implementing, but we can discuss it later. So probably that's exactly actually on time. So let's stop here. So have a good break. Have fun. Okay, one other announcement. Sorry, like I'm always like I will not be here the week after the fall break. So unfortunately, so actually the whole week I'm in Korea. So attending this, it's the best conference in my field, SOSP. So I will be there. So, and I cannot teach just because in Korea, the time zones are so weird. So then this is why I will assign more homework. So please work on it. And then I will be back. But I will, what I will do, I will make myself available for office hours. So you can ask, we can discuss homeworks. And the deadlines will be far away after, but still I ask you to work on those. So we can like quickly catch up after I'm back. Okay, thank you.